Okay, so we're now in the second part of lecture 2, and we want to talk about what does early mean. So I've already discussed that the very earliest universe, up until 380,000 years, lots happened. The Big Bang occurred. There were ionized particles flying around. Eventually, the universe became transparent, and then for a long time, 400 million years, nothing, very little light in the universe. So contrasting 380,000 with 400 million years. Then things get interesting again. We do know some things about the very earliest time, and we're going to talk about those. In fact, using accelerator physics, that is big machines like the one in Europe called at CERN, CERN, they look back to times measured in billionths of a second after the Big Bang. That means the energy levels that they are looking at in the accelerator are enormously high and are comparable to the energy level of particles in the very early universe, when everything was going near the speed of light and there was shrapnel everywhere. So here's another chronology. I know, hard to read, but I'll show you it in detail. This is a chronology of the first few minutes. Once again, Big Bang here and time advancing downward. So what I've done is I've expanded this piece right here in this panel. This goes to the time of 10 to the minus 10 seconds. That's a tenth of a billionth of a second. And this area in here there's some techniques for studying this, certainly theory, but also using accelerator physics. And let's take a look at the temperatures involved. So back here, at the very earliest time, the temperature is 10 to the 32 Kelvin. That is 10 with 30, a number with 32 zeros, a 1 followed by 32 zeros. That's really hot, enormously hot, but getting cool very fast. So it only took, a tiny fraction of a second to go from that stupendously high temperature to a different stupendously high but smaller temperature, 10 to the 29th Kelvin. And then if we wait till we're at a tenth of a billionth of a second after the Big Bang, now the temperature's dropped as well. This is an illustration of the time. I think that's 10 to the minus 32, if you count the zeros. Now, this panel is this part of the drawing on the left, and it shows time still advancing when we finally, pieces of what will become atoms can form, and that allows eventually atoms to form. We're now at a thousandth of a second, and nucleosynthesis is starting. That is, the Big Bang is producing atoms of different sizes, and we'll talk about this in some detail. And this goes on until from a thousandth of a second to 5 minutes. And during this time, the universe is filled with the nuclei of the gases that are going to become prominent, mostly hydrogen. And it stays that way till we get to 380,000. So that number keeps popping up over and over again. Now something else happened. Now this is one of these backward drawings. Very early time on this drawing is on the right, 10 to the minus 43, so time is advancing to the left. And the current theory is that in the earliest universe there was a single force. We'll talk about the ones that exist today in a second. A single force that dictated everything that was going on, and as the universe cooled, a divergence occurred. Gravity, which is the weakest force we know of in our current universe, it's very important, but it's very weak compared to the others. Gravity separated and became an independent mechanism of force. But these others, which include the strong force, which holds the nucleus together, electromagnetism, which is the foundation for all of the electrical technology we have in our society, and the weak force, which is related to decay, radioactive decay, they separated out very quickly. We're still talking about 10 to the minus 10 seconds. These guys are called the grand unification theory forces. People are constantly working on this to try to write down mathematical terms the original force, which included gravity and the other three that we see today, by having sometimes called the theory of everything. Not a success so far. Gravity remains a mysterious outlier. Now, as I did in the first lecture, I turned this around, so early time is on the left and more modern time is on the right, and you can, I know the writing's backwards, but that's just the way it goes. Here's that original force, and then here's the partition of the forces that we currently see. Gravity, the weak force, electromagnetism, and the strong force. Hubble, looking way back, can get back to here. So this is time in the age of the universe, 13.4 billion years from the start. Remember, the universe is only 13.77 billion years old. But Hubble looks back to here. And I've done us a little, remember, everything's moving away from us, and the most distant thing's moving away the fastest. So Hubble has, the oldest thing it's seen is back there at 13.4 billion years ago. 0 is now. So this is just after the Big Bang, in the Dark Age, just at the end of the Dark Age. And I plotted this out for us to look at. Notice this number Z. We don't have to get too technical about it, but this time, just after the Big Bang, has a Z associated of 12. So now let's look at this drawing. What do we see when Z is 12? It says that objects with sending us light at that time, they have a velocity relative to us of about almost 0.99 the speed of light. That's what this dotted line is. This is the velocity of distant objects as a function of this Z number, which is it's an abbreviation that astronomers use. But the point is, the object that Hubble looked at, found, we don't know if it still exists because it produced its light 13.5 billion years ago, but if it exists, it's going away from us at something close to 99% the speed of light. You've seen this picture before. Here's on the left, this is cosmic origin, transparency at 380,000 years, the Dark Age, and so forth. So in the original bang, tremendously high energies and brightness, pieces of the subatomic particles flying everywhere. Then we have cooling enough that atoms can form, and then darkness for a long period of time. And eventually, not for this lecture, eventually the stars formed in the Dark Age started heating up the universe and things changed. We'll talk about that. So this is a depiction of what was going on very early. Once again, there's the 380,000 year boundary. Over on this side, at the high temperatures, just shrapnel. On this side, atoms. So now, finally, let's talk about nucleosynthesis, BBN. The first attempt to explain this happened in the late 40s, and let me show you what this is. This is the array of atoms that exist in our universe, starting with hydrogen, helium, beryllium, bismuth, oxygen, carbon, and the heaviest atoms are over here. And this shows us the abundance. If you added up all the atoms in the universe, and this is something astronomers try to do, the relative abundance of hydrogen is most abundant, lead not so much, and this is not a linear scale. There's iron. There's a reason iron pops up, because it can be produced in stars like our sun. The rest of these things are heavier than iron. So we have this data, and it's gotten better and better since the advent of modern astronomical telescopes. And in the late 40s, George Gamow, who for part of his career was at the University of Colorado in Boulder, he had this idea that the early universe produced all the atoms that exist, this whole array of atoms. Everything from hydrogen up to thorium, I guess, is the heaviest stable atom in the universe. So he said to his students, see if you can come up with a theory of an early universe that produces the abundances observed on this chart. And by the way, this is done by looking at galaxies and looking at the spectra of galaxies and taking note of how much of each kind of atom is observed. And the students came back and they said, in spite of his genius and his reputation, they said, Professor, you are wrong. Most of the elements that we see today could not have been formed in the early universe. This was a shocking result. And it has to do with neutrons. So if you remember your high school chemistry, neutrons are involved in virtually all atoms except hydrogen. And the neutrons are embedded in the nucleus of atoms and are partnered with protons to define the properties of the nucleus of various kinds of elements. And what Gamow's students found, that neutrons flying around in the early universe were needed to build these heavy elements. But there's a problem. Neutrons, isolated neutrons, are not stable. They decay, sort of like a radioactive decay thing, with a half-life of something like 9 minutes. So if you can get a bottle of neutrons, and people do this, you get a bottle of neutrons and wait around 9 minutes, half the neutrons are gone and have become protons, and other little particles are produced in that process. So a lack of neutrons meant that these heavier elements, which require protons and neutrons to build them, there was a deficit of neutrons in the early universe. So in the few minutes that the universe had to build all these elements, according to Gamow's guess, in those few minutes, it just wasn't time because the neutrons were gone. And where'd these other things come from? They were made in stars. So when we talk about what went on in the early universe, we're confining ourselves to this little group right here. Hydrogen, helium, lithium, beryllium, a little bit of boron. But I think by the time you get to carbon, just the early universe did not have anything from carbon on up. Now, important byproduct of Gamow's students, this is at Georgetown University in the late 40s. An important byproduct is his students realized that the Big Bang, which was still controversial at the time, if it existed, we should be able to detect the afterglow of the explosion. I want to be careful about using that word explosion, because explosion, we all have seen in action movies. That's an expansion of a thing, like a bomb, into a pre-existing space. The explosion I'm referring to is not that. It is the expansion of the universe from being invisibly small and the universe getting bigger. So we'll be saying this over and over, that the expansion of the universe is not an event where something is expanding into a pre-existing volume. It's expansion of the volume itself. Nonetheless, Gamoff's students predicted that if we looked at the sky with the right instrumentation, we would see a bath of radiation at about 5 degrees above absolute zero. That's 5 kelvins. And so by 1952, that little group at Georgetown had worked through this. Here's a picture of George Gamoff with he was like an impish fellow. Practical jokes and cartoons and poems. And this one's particularly interesting. It says, "Twinkle, twinkle, quasi-star." That's a bright object that was seen but unexplained in his lifetime. "Biggest puzzle from afar, how unlike the other ones, brighter than a billion suns. Twinkle, twinkle, quasi-star. How I wonder what you are." And we now know what quasi-stars, also called quasars, we know what they are. They're the accretion disk of supermassive black holes in the nucleus of almost, probably all, galaxies. But in George Gamoff's time, these bright objects were just a complete mystery. And we took a picture of one last year, and we will talk about that. So, Big Bang nucleosynthesis. We need a theory that predicts the amount and rate of production of light elements, hydrogen, helium, deuterium, which is heavy hydrogen, beryllium, and lithium. And a theory exists. It was created to a large degree by Gamoff's students, and it looks like this. So here's time from the beginning of the universe in seconds. So the Big Bang is down here at 0, which doesn't appear on this chart. So that's 1 second, 10 seconds, 100 seconds, so kind of like a minute is in here. Actually, I think I have labels for these. And here are the temperatures in billions of kelvins. 10 billion kelvins, 1 billion, and so forth. So you can see on a time scale of 100 seconds, the universe went from being immensely hot to just stupendously hot. And here's how the abundance, this is the frequency of finding different kinds of elements, occurs. Incidentally, 100% is right there. For some reason, they made this art go above there. That isn't right. There's 100% right there. And almost all of it is hydrogen. We'll skip this for a second. Y sub p is the astronomer abbreviation for helium. So you see that during this, the theory says that during the evolution of time in the early universe, the amount of helium increased from near 0 and it kept rising. And then it got to a number, which I will tell you soon, and then it stopped, that abundance stopped. This end thing, well, I have to admit, those are the neutrons, just fading away. So they start out with this high abundance, and after some minutes, it faded down, and eventually free neutrons kind of disappeared in the universe. And yellow here, deuterium, here's an isotope of helium, hydrogen, beryllium, and lithium. So we have this model that Gamoff and his students developed, and the question is it right? So, pointed out that tick mark is at 100%. There's 1 second, 1 minute, 1 hour. A lot happened in the first hour, and there's 1 day. Those are the neutrons. Here's a cartoon of what goes on to produce helium. So a proton and a neutron get married, and that is a deuterium nucleus, and that throws off a little piece of light called a photon. And then 2 of these guys, they get married, so this is a polyamorous kind of situation. 2 neutrons, they get together and they produce something called hydrogen 3. And the hydrogen 3 runs around the singles bar for a while and then finds another deuterium. And that gives it enough protons and neutrons, and we have helium. And this key shows you the neutrons and the protons. It's a little more complicated, but the idea is if you group together enough heliums and hydrogens, you can account for what's going on in the universe. And this little chart predicts what fraction of the universe should be helium. And if you do the arithmetic implied by the drawing, which we will not do, it says helium should represent 75% of the mass. Sorry, the hydrogen to helium ratio should be the ratio of 12 to 4. So there's a lot of hydrogen in the universe, but it's very light. And this drawing shows you how to calculate. So let's see. And here's a drawing, sort of more technical drawing of what I just showed. A neutron, a proton, deuterium. Deuterium interacting with helium-3, you get tritium. And if you have the right particles, you get helium. And if the helium is if a helium-4 is struck by helium-3, we get lithium. But we can also get beryllium from this process. And notice arrows are going all over. It's complicated. Here's some of the equations. These were created in the early 50s before big computers were available. When Gamow and his students were doing this, there might have been 2 computers in the United States capable of helping with this problem. A lot of this was done by hand. So this, once again, no need to go through the detail, but it shows the objects that were created: helium, lithium, deuterium, beryllium, and so forth. And it's complicated because when this happens, this thing here, you get deuterium, which goes over here, and it has an interaction with this. And then if you keep looking, you'll find all these things are coupled. Very, very complicated. That's a symbol for yikes. And the theory works great, with one exception. So here's what the theory predicts. We have this gray bar. We can slide this back and forth and compare the theory with what's actually observed in the universe by looking at galaxies. And if you position this bar, which is the fraction of the universe that's made of the stuff we're made of, if you position that bar in the right place, you can get very good agreement with what is observed. So here's deuterium. If you pick this value for the fraction of the universe that is atoms, you get a prediction that deuterium is somewhere like in here, and the horizontal orange bar is the measured value for the amount of deuterium in the universe. Similar, helium-3, right in there. Lithium is a problem because the prediction is lithium would be somewhere in this range. But lithium is down here. And that's been a mystery. There's work being done to understand what is the deal with lithium. And there's some ideas. But the most important result of this is that the best match for all the elements in the early universe comes by picking this number for the fraction of the universe that is ordinary matter. And when I say ordinary, I mean it's the stuff we're made of. It's not dark matter, which is a topic we will get to. So if you pick this number, things work. And that's really significant. And we will talk about this over and over again in future talks. So this is a chart that provides some clues for me if somebody wants to talk about the lithium problem. This is something we can use this chart. Now, as a result of the work of Gamow and his students, and eventually a lot of other people, we now have this version of the periodic table of elements. All of you saw this in high school chemistry. You have the lightest elements over here, hydrogen. We have helium, lithium, beryllium, and this is organized, in a way that explains all of chemistry. But what's important now is because of Big Bang nucleosynthesis theory, we now know we can calculate how much of the universe is made of different elements. So here's this blue. Anything that's blue was made in Big Bang. This kind of melon color is related to cosmic rays crashing into the atmosphere of planets and stars. Green, that's a place where low mass dying stars produce. If you look across here, you'll see a lot of these elements are made in low mass dying stars. Some is made in exploding stars, white dwarfs, neutron stars, and this kind of gold color is humans create this in reactors. All this stuff does not occur naturally. So if we look through here, we see helium, all coming from Big Bang. Lithium has this fraction from the Big Bang, and some from cosmic rays, and some from dying low mass stars. Sodium, virtually all of it comes from massive stars. Magnesium, calcium, rubidium, so forth. So as you scan through this, you can see, like here's a whole row of exotic elements that are found on Earth, but were not made in the Big Bang. They were made in exploding massive stars and found their way to our planet and Krypton. Not kryptonite, Krypton. This to me is sort of an astounding chart. A particularly interesting one here is iridium, made in neutron stars. This plays an important role in understanding if and when dinosaur extinction occurred because an asteroid struck our planet. Because iridium is extremely rare on our planet, except where it is associated with meteorite impacts. The universe is, whatever iridium exists in the universe, it's just flying around trapped in rocks. Our planet was born without a lot of iridium, so this provided an enormously helpful clue in diagnosing the death of the dinosaurs. So, let's talk now about the structure of atoms that existed right after the universe cooled to a point where atoms could exist. So we're going to stop here. This is the end of part 2.